Today we're going to be talking about ratios of areas. So let's talk about the area of triangle ABD. Okay, let's call the altitude let's call that the H for height. So the area would be 1/2. Our base of ABD would be side AD times by my height. Now triangle BDC. In relation to side DC, which I'm going to call the base, our height is that same segment H. So we'd have 1/2 DC times H. The 1/2's cancel, the H's cancel since they're the same thing. So we have AD to DC. So what this means, if we have the same height, if two different triangles, share a common height, the ratio of their areas is going to be the ratio of the bases. Let's look at a different example where triangle WZX and WYX share the same base. Okay, so the area of the first one, let's call this height 1. So I have 1/2 height 1 times by the base, which is WX. The area of the other triangle, WYZ, 1/2. Well, they have the same base, but now I have a different height. I'll call that H2. So we have the 1/2's canceling, the WX is canceling, so we have height 1 to height 2. So if we have the same base, then we have the ratio of the areas is the ratio of our heights. Okay. Area of triangle MLR. So I have this triangle here in relation to triangle MPJ. And I've told us that angle L is equal to angle P. Okay, so you'd have to be given that. We also know angle ML, I should say, and PML are also equal because they're vertical angles. So these are similar triangles. So now we're going to be talking about if we have similar triangles. Okay, and you'd have to know that L and P were equal. I forgot to highlight that at the beginning, but L and P are equal. So we have, for the top triangle, we have 1/2 our base, which is RL, times by the height. Again, I'm going to call that H1, over on the other triangle. We have 1/2. I'm going to call our base is JP, times by the height, which is H2. So again, the 1/2's cancel. So RL and JP, when you have those ratios, okay, RL over JP, that's the scale factor. And the ratio of RL to JP is the same thing as H1 to H2. So what that means is that is the scale factor squared. Since RL and JP are the same thing, I'm sorry, are corresponding sides and are similar triangles. When I'm talking about their ratio, I'm talking about the scale factor. And same thing for H1 and H2. The heights are going to be proportional. We actually proved this way back when we were talking about similar triangles. So when you're looking at the ratio of areas of similar triangles, it's the square of the scale factor. And here is what we just discovered, or what I just explained, in all of those three cases. Make sure this is written in your notes. Students often forget to write this in their notes, and then they're really confused. Okay, so please make sure you write this in your notes for me. Okay, so let's do a few examples. ABD, ABD, triangle ABD to triangle ADC. They technically both share the same height of AD. So if they have the same height, it's the ratio of the bases. So the ratio of the bases, the ratio of ABD, our base is BD, so that's 12, 2, and then ADC, 9. I reduced that ratio 4 to 3. It's the ratio of the bases. Now ABC to ABD. So the smaller triangle in here, ABC to ABD. Again, they share the same common height. So it's going to be the ratio of the bases. BC is our base, so that's 3 to the whole base, which is 12. Reducing that, that's 1 to 4. Now here, RST to PST. They share the common base now. So now we have an example where we have a common base. So RST to PST, you would compare the heights. So our height for the top one is 9. Height for the bottom one is 3. So that would reduce to 3 to 1. And then XRT, the side triangle, XRT to XPT. Okay. Again, they share the same common base of XT, so it's the ratio of the heights, which is 9 to 3 or 3 to 1 because we reduce. Okay, if the scale factor of two similar figures is A to B, then the ratio of their perimeters is also A to B, and the ratio of their areas, you just have to square the scale factor. Okay, so the ratio of the perimeter is A to B, and then you square it to find the ratio for the areas. Okay, this example. Two similar triangles have an area of 144 and 169. If a side of the larger triangle is 26, find the length of the corresponding side of the smaller triangle. So two similar figures. I'm going to call this A. I'm going to call this B. So there's scale factor. So the scale factor of A and the scale factor of B is equal to the ratio of their areas. So we square root both sides. So we get A is to B as 12 is to 13. So here now, the side of the longer triangle is 26. So the side in B is 26. So I need to solve for A. Really, if you think about it, we're just multiplying by 2, so therefore A is going to be 24 centimeters. Okay, our last example, and this one is modeled after a question that you guys have in your book, and I always like to put this type of question on the test. Okay, so we have a trapezoid. Remember, our trapezoid has parallel sides. So find the ratio of the areas of 1 to 3. So of 1 to 3. Okay, remember we have parallel sides. So this angle and this angle there are congruent. And our vertical angles are congruent. So 1 and 3 are actually similar. So it's going to be the square of their scale factor. So the scale factor is 5 to 10, or 1 to 2. But remember, it's the square when we're talking about similar figures. So the ratio of their areas is 1 to 4. Now 1 to 2. What might be challenging for some of you guys to see, and you might have to kind of turn your triangles around. But 1 and 2 technically share this common height. Okay, so that means it's going to be the ratio of the bases. Now, you have to remember that 1 and 3 are similar, and their scale factor is 1 to 2. So this side right here, in proportion to this side right here, since this side that I'm highlighting in green is also in triangle 3 and 2. The ratio of their sides is 1 to 2. Okay, because it's the scale factor between the two similar triangles of 1 and 3. This green side is the base in triangle 2, the red is the base in triangle 1, so my ratio is 1 to 2. Same thing holds true when we're comparing 1 and 4. Let me do a little bit of erasing here. Okay, now between 1 and 4, you guys might be able to better see the altitude that I draw in. When I draw in my height or my altitude, again, it's going to be the ratio of the bases. I have one base here. Again, the ratio of that purple side that I have highlighted to the green side is going to be 1 to 2, because this is 1 unit, and it's in triangle 1, and this is 2 units, because it's in triangle 3, which is similar to triangle 1, but this green side is also in triangle 4. So that's why it's also 1 to 2. Now, look at 4 to 2. Well, let's look at it this way. Okay, I'm going to essentially kind of put in some numbers. So if the ratio of 1 to 3 is 1 to 4, so say his units is 1. He's 1 time, this guy's 4 times that. 1 and 2 are in relationship of 1 to 2. Same thing with 1 and 4. Now what's 4 and 2's ratio? That's going to be 1 to 1. Now 1 to the whole trapezoid. If this is 1 unit, so that's 1 unit, is to the whole trapezoid. We'll look at these as like possible potential areas. That's 1. These are both 2, so that's a total of 5 plus the 4, so the whole area of the trapezoid would be 9. So we're looking at a 1 to 9 ratio of our areas. Okay, there are your 2 lesson questions. Please make sure those are submitted on time.